Okay, so this is video 2. We're going to look at diving physics. I was just with you discussing scuba equipment. So here we go. How many of you have experienced the popping of your ears when flying or felt that pressure when diving to the bottom of a swimming pool? Well, these pressures are all associated with some form of diving physics. All right, so what we're going to look at now, we'll go over common measurements used in diving. We're going to look at the density of air and water. We're going to look at the common and general gas laws associated with diving and pressures. When we enter the underwater world, many things that we consider normal no longer seem to apply. Common sense tells us that a dropped object will fall to the ground, but underwater, it may rise rather than fall. Many people see physics as challenging, if not a daunting subject, due to being uncomfortable with numbers and mathematics, but we use them as tools to better understand and describe what we're observing. And the goal is to understand the principles of physics as they affect us in our diving. Okay. So, basic principles of gas. We know matter, it takes on 3 forms: solid, liquid, and gas. Gases we're looking at, specifically with diving, gases are compressible and fill containers. They're also affected by temperature. Gas mixtures are made up of individual gases, and once mixed, they stay mixed and are hard to separate. One thing to note is gas dissolve in liquids in proportion to pressure. In reference to this is why you limit your ascent rate, because if not, the gas that did not have time to dissolve is allowed to be released out of your body in gas bubbles into your bloodstream, and that is what causes DCS. We'll look more into this topic when we get into Henry's Law. DCS is decompression sickness, but we'll look at it when we get into Henry's Law. Okay. Gases in diving. One thing to note is air. Air is actually comprised 78% nitrogen. That's the most plentiful component of air. It's colorless, odorless, and tasteless. Another component of air is oxygen. Oxygen makes up about 20.9% of air. Oxygen is a life support gas. It also is colorless, odorless, and tasteless. The other, about 1% of air is argon. Carbon dioxide, it makes up 0.03%. It's a byproduct of our respiration. It's also colorless and in low concentrations, odorless and tasteless. You'll notice that's a common characteristic between these gases. So in putting your scuba kit together, you want to make sure that if your air has a taste or smell, then that should be your first sign that something is wrong and should get that checked out, before the dive. Okay, next is measurements. Length is the distance between 2 points. Area and volume are determined in units of length. Area is actually measured in cubic feet, and volume, air is measured in square feet and square footage, and volume is measured in cubic feet. Okay. Next is mass. Mass is the property of a body that is a measure of its inertia, commonly equated to weight. Time times measured in either seconds or minutes. Energy is the capacity to do work. Energy is also associated with temperature, which is a measure of hotness and produced by average kinetic energy of the molecules in the body. All right, force. Force is any action that tends to cause change in a body, change in motion of a body, or to distort it. All right, there's two systems of measurements that could be used in diving. The SI system, or commonly called the metric system, or the imperial system. That's what we primarily use in the US. Feet, minutes, second, things of that nature. Okay, now we'll look at density. Density is mass per unit volume. In the SI system, it's expressed kilograms per liter. In the US system, or imperial system, it's expressed in pounds per cubic foot. All right, so we look at the density of fresh water. It's a 1 kilogram per liter, or 62.43 pounds per cubic feet. Density of salt water is 1.029 kilograms per liter, or 64 pounds per cubic feet. The density of dry air is 1.2929 kilogram per cubic meter, or equal to 0.0807 pounds per cubic foot. Let's see, two phenomena of water density that are encountered by divers is the thermocline and halocline. Whereas the thermocline is the warm water that is allows the less denser, it's the warmer, less dense water that is able to float on colder, denser water. That's one phenomena. The other phenomena is the halocline. That's actually fresh water being able to float on salt water. Salt water is more dense. Fresh water is less dense. Okay. All right. Now we'll look at buoyancy. Buoyancy is the force that allows lighter objects to float and heavy objects to weigh less when submerged in water. Okay, in other words, an object that is denser than water will sink because the buoyant force of the water is not enough to support it or push it to the surface. But also, any object will weigh less in water than out of water because of the upward force of buoyancy provided by the water. This is how we get into Archimedes' principle. Archimedes' principle states an object wholly or partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced. Okay. When a diver floats or sinks or hovers, it's a result of the combined forces of the weight of the diver, the downward force, and the buoyant force, the upward force of the displaced water. Okay. This also explains lifting underwater. Buoyancy can be used to raise sunken objects from the bottom. These lifting calculations actually use Archimedes' principle. Okay. All right, now we're going to look at pressure. Pressure is the force acting on a unit area. P equals force divided by area. In the US, it's measured in pounds per square inch, or PSI. All right, as divers, we often use atmospheres to measure pressure. Pressure at the surface is 1 atmosphere, while the gauge shows 0. Ordinary gauges show the pressure in excess of atmospheric pressure, distinguishing it from absolute or total pressure. Okay, you see from the chart here where your absolute pressure, 1 atmospheres, is at the surface where your gauge shows 0. So if you go down to 33 feet or 10 meters, that's where your atmospheric pressure is 2, where then your gauge pressure would show 1, and so on and so on. All right. Next, we'll look at partial pressure. Partial pressure is the effect of a single gas component in a gas mixture. As I mentioned earlier, if you look at air is composed 79% nitrogen and 21% oxygen. So your partial pressure is the 0.79 atmospheres, and that's multiplying by 1. All right, fraction of the component gas, when added, all of the partial pressures of the component gases becomes the total pressure. So that's where you get the 0.79 atmospheres plus the 0.21 atmospheres oxygen equals the 1 atmosphere. All right, now we'll look at Dalton's law. In a mixture of gases, the total pressure is made up of the sum of the pressures of the individual components. And that formula is stated: P, total pressure, is equal the partial pressure of 1 plus the partial pressure of the second gas plus the partial pressure of the third gas out to the partial pressure of the nth gas. All right, another way to calculate that formula is the partial pressure of the gas is equal to the fraction of that gas times the total pressure. All right, next, looking at Boyle's law. Boyle's law simply states as you increase the pressure on an object, the volume decreases. They are indirectly proportional. So if you take a balloon, you submerge the balloon, as you increase the pressure on that balloon, or the air, the pressure increases on that balloon, the air or volume inside that balloon decreases. Okay, Boyle's law. Next is Charles' law. Charles' law simply states at a constant pressure, as you increase temperature, volume increases. As you reduce temperature, volume is reduced. So this law is saying the volume is directly proportional to temperature at a constant pressure. Okay. The Gay-Lussac's or Hamilton's law, it has to do with pressure and temperature. So it's saying at a constant volume, as you increase temperature, the pressure increases. And as you reduce temperature, the pressure decreases. That's like if you had a scuba cylinder in a hot car. As temperatures rises, the pressure in that cylinder uptakes a little. Okay. Next is Henry's law that I was talking about earlier. Henry's law simply states that a gas is soluble in tissue as you increase pressure. All right. As you decrease pressure, that gas is able to be released from the tissue in your body. Okay. So essentially, if we ascend too fast, the nitrogen gas built up in our tissues will be released into the bloodstream in the form of bubbles, calling decompression sickness. Okay. Henry's law. All right, in the general gas law, it's a combination of Boyle's law, Charles' law, and Hamilton's law combined, and that's used to predict the behavior of any quantity of gas in terms of pressure, volume, and temperature. So that formula, as you notice below, pressure times volume divided by temperature is equal to pressure times volume divided by temperature. Okay, pretty self-explanatory there. Okay, so in summary, we learned the common measurements, both US and the SI system. We learned about density of air, water, both seawater and freshwater, and understand how the water density affects diving, which is Boyle's law. We learned the Archimedes principle and how to apply it to buoyancy problems. We learned about pressures, both absolute and gauge pressure. We learned about the major component of gases of air and what their percentages are in normal air. We learned about several gas laws that pertain to diving and can solve problems associated with them. More in-depth information can be attained by taking the NAUI Master Scuba Diver course. So I'm going to take a break here before we go into the next section, decompression theories and dive table.